All right, we left off with this little conundrum. So we looked at the different R values we get for potential fundamental frequencies for our little snippet of a waveform. And we found that the best R value, or the highest R value, came at 195 hertz. And the second best one we found at 98 hertz, which for whatever reason is only half of our best candidate, which seems kind of funny. So why would that be the case? Why would we be getting this weird sort of matchup where it's half, the second best candidate is half of the best candidate? And you can kind of see that if we go back to how we set up our analysis with the three potential frequencies, 100, 200, and 400 hertz. So if we look at 200 hertz as a potential fundamental frequency for this waveform, we start our 200 hertz window at this spot. And we can see that matches pretty well to the original, right? So we start low, we go through this little bump in both cases, then to the big bump, and then to the series of smaller, decreasingly smaller bumps after that in the complex wave. So that's a fairly good match, right? But if you think about it, this is where 200 hertz begins. It's a period of 1 over 200. If I'm looking at 100 hertz, or half that, my frequency is half as high, but my period is twice as long. So if I just go one more period over here, that puts me in almost exactly the same spot in the overall cycle of this complex wave in terms of where it begins and ends. So this is actually where we started for a period of 1 over 100 hertz. And again, we found a pretty good match. It's not as good because maybe the timing is a little bit off, and also the complex wave looks a little bit different from this initial one, but it's pretty close, right? So what's happening here is that the matches, the best matches in terms of the R value will happen at regularly repeating points in time. The first best match ideally should be where the next repetition of that cycle begins, and the second best match will be right where the next repetition of that cycle begins. And if we kept looking further and further down the line, longer and longer periods, our next best match will probably be here where this third repetition begins. And that would be a further reduction in the overall frequency. And so instead of like 1/2 of the actual fundamental frequency, it would be 1/3, which would be about 67 or 65, something like that. So that's actually too low for our analysis. We didn't get there. But you'd see it pop up here somewhere along the line. So we kind of get this blah, 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 and then we get another blah, 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 somewhere over here. We just didn't actually analyze that frequency. That's what's happening. It's capturing that second best candidate, which is the second repetition of the fundamental cycle. The best candidate is the first repetition of the fundamental cycle. So this also answers the second question I posed to you, which is what happens if we set the upper end of the frequency range to 150 hertz and we just look at this set of R values. In that case, the pitch tracker is going to think that this is the fundamental frequency. It's going to think that 98 hertz is our best candidate and tell you that that is what the best match is. So that's like starting our pitch tracking analysis with our shortest period being here. We never look at this first potential glottal pulse just because we don't know it's there. We're just starting with our frequency range here, and we're looking down here at shorter and shorter period, longer and longer periods, lower and lower frequencies. And our best match is this second repetition. We just never see that one at all. And if that happens, if you put the top end of the frequency range for the pitch tracker too low, you get this phenomenon which is called pitch halving. And it occurs when the shortest period checked is longer than the fundamental period in your complex waveform. So the pitch tracker's next best guess will be that the fundamental period is twice as long as it is in reality. And if that fundamental period is twice as long as it is in reality, then it's going to estimate F0 to be half of its actual value, because twice as long of a period is half as much of a frequency. So you can almost always fix this by expanding the high end of the frequency range in the pitch tracker settings. And I'll show, so I'll pose this question of why does it work? And I do want you to think about it, but I'm going to show you why it should work. Again, going back to this slide. So this is our like if we have our shortest period check somewhere around here, then our best match is going to be basically where this blue waveform begins. And if I am, and the problem there again is that we're just not even seeing this first match because we're just starting our analysis here and only looking in this direction. So if I increase my frequency range at the high end, if I'm looking at higher and higher frequencies, then I am going to be looking at shorter and shorter periods. And hopefully I'll get it short enough that I'll be able to catch this first repetition of the pattern. I'll be able to analyze windows like where this blue one starts here. That's what increasing the high end of the frequency range buys me when I change those settings in my pitch tracker. So I'll show you what this looks like. This is a common problem. Doesn't happen all the time, but happens enough. So this is this initial sample that I played for you before.
Yeah, the thing is that like if you only met him for like a day, you would think he was totally normal.
So that was a little loud, but we'll play it again. So the highest part of this F0 contour is in this particular utterance here.
Yeah, the thing is that like if you only met him for like a day, you would think he was totally normal.
I forgot what word that was, but it's thing. Her F0 goes quite high there. And if we look at that in the appropriate pitch track, we can see that big bump, right? But here in this one, the pitch is halved. So I don't know what this is. It's like maybe 350 hertz or something like that. In this analysis, it's going to tell you it's like 175 hertz or something lower than that, than the actual value. And the reason is because I have set my upper end of the frequency range too low. So in this analysis, I've got it at 400 hertz. Here it's at 300. So it's not even going to consider a frequency this high. And instead, its second best match is going to be here at half of the actual value.
Yeah, the thing is that like if you only met him for like a day, you would think he was totally normal.
So you should be able to hear that the thing goes really high, but it doesn't look like it's going high in the pitch tracker. So for that reason, number one, you should know that something is off. And the other reason that you know something is off is because you get this weird effect where this is dramatic jump down and then another dramatic jump back up, even though that is not kind of a normal way that the human voice works.
Yeah, the thing is that like if you only met him for like a day, you would think he was totally normal.
And it doesn't sound like what you're hearing, right? So that is pitch halving in a nutshell there. And again, the fix for that is to increase the pitch range at the high end to something that can sort of encompass or figure out what sort of high pitch is actually being produced here. And then you're set, right? So this is a problem. This is why it occurs. This is how you fix it. Watch out for that because we're going to be using these pitch contours when we do our analysis of intonation starting in the next set of lectures. Okay, so it's also possible to get the other problem, which is called pitch doubling. It just very rarely happens. So pitch doubling would occur if the shortest period checked is less than half of the fundamental period. And then also the second half of the fundamental cycle looks very similar to the first. It basically looks like kind of say if you had two sine wave, like a sine wave where you have one big bump and one little bump in your fundamental cycle. Maybe I'll draw you an example when I can make another video and pick up my whiteboard. But if those two halves are very similar to the first, it might look like you get two fundamental cycles rather than one. That doesn't happen that often though, which is why I'm not going to bother with the whiteboard right now because you normally don't have to worry about that. But if this does happen where the shortest period checked is less than half of the fundamental and the second half looks close to the first, then the pitch tracker will think the fundamental period is only half as long as it actually is. It's kind of catching the second bump in the fundamental cycle as like what it thinks the first bump of the next repetition is. So it will display F0 to be twice as high as it is in reality. Like I said, it's not as common of a problem as pitch halving, but there's no easy fix for it. If you do see it, you just kind of have to watch out for it. In fact, I don't really have a good example from anything I've done recently. This is an example I borrowed from a website on intonation transcription from a long time ago. So it uses a different pitch tracker here, one that's called X Waves, and I don't know if they even use it anymore. But I'll play this for you, and you can maybe hopefully hear that the pitch tracker is doubling here as we go through this phrase. Then I don't know if I can explain it to you.
Then I don't know if I can explain it to you.
So his pitch doesn't actually go up that high here, but it just looks like it's going up high in the pitch tracker.
Then I don't know if I can explain it to you.
Going back to the moral of the story from digital signal processing, when we look at pitch tracking, we're looking at a representation of reality. It's not actual reality, and it can produce some illusions sometimes, and you just have to know what they are so you don't get fooled by them. Another illusion you can get is something called micro perturbation. So this is the result of the fact that the speech waveform you're looking at, the waveform that the pitch tracker is trying to figure out the fundamental frequency of, that waveform is shaped a little bit by the type of segment being produced. So the waveform itself has characteristic resonant frequencies, as we talked about in 341, and they're going to look a little bit different for different vowels. They're going to look a little bit different for different segments, like sonorants versus obstruents, that sort of thing. And for that reason, pitch tracking can become a little bit erratic at the juncture of two different types of segments. In particular, you get this when you're going from like voice to voiceless segments, or for sonorants to obstruents, that sort of thing, or for like vowels to nasals. So what you see there are little bumps in the F0 contour sometimes, and they're known as micro perturbations. And those, again, well, they're not necessarily illusions. They represent some acoustic reality in the signal. Your job is not to get misled by them and not to think that they're more important than they actually are. And I'll give you an example here in a second. Before I do, I'll also point out that in addition to these two problems, you often get a problem when you're going from like modal to creaky voicing or back and forth, because creaky voicing just look kind of fundamentally different from modal voicing. So I've got an example here of that from my mom. Yeah, so actually I'll show you. This is the snippet that we were playing around with. Yeah, and as you can see, over here in the pitch tracker, it thinks that the fundamental frequency is 195 hertz, just like we figured out from our pitch tracking analysis. I'll play the whole thing here.
This night it's going to be about Norwegian and German farmers coming to the Midwest. Well, anyway.
Yeah, so this is where that snippet came from. And if we zoom in on this, I think it came from like 1.85 seconds, like around here. Yeah, so this is like, it's guessing when you look at it in context that the fundamental frequency is a little bit higher than what we analyzed, like 198.8. That's part of how PROT works as well when it does pitch tracking. It doesn't make huge jumps, and it kind of smooths over the curve as it calculates F0 from one spot to the next. So it's not exactly the same. There's a little more going on behind the scenes, but we don't really have to worry about that. I will also point out this part. So she has a little bit of creaky voice in here at the start. And you can hear that at the beginning. So we get this dramatic leap here. This is a little bit more than a micro perturbation. This is like a creaky to modal voice perturbation. But your job is to not read anything into this. She's not like targeting this F0. She just happens to have a bit of creaky voice here at the start. And that gives you this kind of discontinuity. What I'm talking about in terms of perturbations or micro perturbations is this stuff. So you can see this is night is. And going from the vowel or diphthong in night to the T, which turns into a flap, basically, you get this little bump here. That's a micro perturbation because the waveform looks a little bit differently here in the middle of the flap than it does in the vowel right before it. So PROT has to kind of adjust a little bit. Don't read anything significant into this either. You can kind of see it, but it's not a big deal. And maybe you can see it a little better if we like grab a bigger chunk of this.
This night it's going to be
this little perturbation. Okay, and you can see it in some of these other like vowel to consonant transitions as well. All right, so you can also, I also want to show you a few other things you can do with pitch tracking in PROT, which are kind of fun. Yeah, so we could play with, this is that token we were listening to.
Yeah, the thing is that, like, if you only met him for like a day, you would think he was totally normal.
Yeah, and if you put this down to 300 at the high end, you get that pitch halving effect, right?
The thing is that
Normally for a female speaker, I would probably raise the bottom end of this to like 100 because it's rare that female speakers go below that. And maybe like 500 at the high end is a good range for a female speaker. But you can kind of read it based on who you're actually dealing with. So some people have a broader pitch range than others. And if you're doing, say, analysis of the F0 for transcribing intonation, which is what we're going to do in the next unit, you kind of want to give yourself the best chance at trying to see where the big important bumps and valleys are in the intonation or F0 contour. So you can squeeze this a little at the top maybe to bring those out a bit more. This is more of an issue for male speakers who tend to have a condensed pitch range, and it's harder to see where sort of the big peaks and valleys come from. I will show you as well. If we do what's called analyze the periodicity of this in Prot, we'll keep it at 75 to 600 here. Yeah, so we'll do it for that one. We'll do it for this movie night snippet as well. We'll look at that one first. So, yeah, this tells me, this is the one we looked at in the example in the lecture slides. This tells me that 195 hertz is my best candidate for this little blup. And my next best candidates is down here. So it's hard to read. So this basically tells you, kind of gives you a quantitative value for where R is kind of reaching a peak. And so 9 is the highest level. This one, it's hard to see, but it's like an 8 here. And it's right at half that, right? So it's 97 is half of 195, and this one is at half that as well. That's where those potential pitch halving errors can come into play. And these are these other peaks we saw in that analysis. So at like 251 hertz, it thinks it's got another peak. So this is that peak right there, and so on and so forth. I'm not going to worry about that too much. I will show you this pitch object. This is kind of fun. Again, we created this by highlighting the sound, going to analyze periodicity to pitch, and then it gives you this analysis of how it calculated what the F0 contour is. You can play it. It sounds like this. Yeah, you probably don't want to sound like that. It's just playing the entire pitch contour on like a schwa, and then leaving out the gaps where it's voiceless. Let's move in a little bit here. We can kind of see the same effect. Like I said, it's highlighting these candidates where it's getting the highest R values. But again, it kind of disprefers making big jumps if it doesn't have to. It's trying to avoid that pitch halving effect. So there's a bunch of like 9s and 8s down here. So where's this one? So this one's at 273. This should be like at what, 137 or so, 136. That's half that value. And like I said, you'd also expect another peak at about a third of that value. So a third of that is what, 91? Yeah, so there you go. There's your pitch thirding. But it's not guessing this. It's pretty smart in terms of how it does this. This is our best R value, and it's also trying to make this continuous as it goes. Yeah. So, but this kind of shows you its analysis, its underlying analysis. And the other fun thing you can do with this is manipulate it. So we'll go change this sound to a manipulation object. It wants to make the time step 0.01. We'll make that 0.1 to make it a little more manageable. And now we get this, which is an abstracted pitch contour.
Yeah, the thing is that, like, if you only met him for like a day, you would think he was totally normal.
And we can change the pitch using speech synthesis in Prot. So there's a bit of a uptalk here contour at the end, or a continuation contour.
You would think he was totally normal.
We can make that a little more definitive by lowering the pitch at the end, so it just kind of descends down to the bottom of the speaker's range. What does it sound like now?
Yeah, the thing is that, like, if you only met him for like a day, you would think he was totally normal.
Yeah, nothing more to say, right? There's this little rise here in the middle too. We could do the same thing with that. Make it sound more definitively conclusive.
Yeah, the thing is that, like, if you only met him for like a day, you would think he was totally normal.
So I don't know how convincing you find that. We can also make it like more clearly a question by just really rising this up at the end.
Yeah, the thing is that, like, if you only met him for like a day, you would think he was totally normal.
Or maybe. Yeah, either way, you can play with this. You can create alternative realities if you want. It might be a little bit dangerous to do this, but it's also a lot of fun. There's limits, though. If you really push it, it sounds more and more mechanical as you go. I will point out, though, that if we go back to where we were, I did do exactly that sort of thing for a research project once upon a time with Mary O'Brien, who's over in German. And what we did is basically we switched, you can transpose intonation contours from one utterance to the next. So we did this looking at native English speaker productions of English sentences and native German speaker productions of English sentences to see if sort of the native German intonation, if we applied it to a native English speaker's productions of a sentence, would make it sound more accented, whatever that might mean. So we have a native English speaker saying,
"Where were you a year ago?"
And we have a native German speaker saying the same thing.
"Where were you a year ago?"
And we just took this guy's intonation contour and spliced it onto the English production.
"Where were you a year ago?"
And then also did the same in the opposite direction.
"Where were you a year ago?"
So there's a question of whether this sounds like it's maybe a little more accented.
"Where were you a year ago?"
And maybe this sounds a little less.
"Where were you a year ago?"
That was the general trend we got. It's a little complicated, though, because the algorithm isn't perfect. But basically the idea is that intonation is part of what kind of contributes to it, the percept of accentedness when you're listening to second language speech. So that's kind of fun, and we'll talk about that more later when we get into intonation in the next unit. Basically, to wrap things up with automatic pitch tracking, the pitch tracker can use 3 parameters. Window size, I should have mentioned this before I didn't, but the window size in prot is always going to be 3 times the longest possible period it's checking. So the default longest possible period is 1/75 seconds. If you multiply that by 3, you get a total window of 0.04 seconds. That's why we were looking at a window length of 0.04 seconds from the very beginning of that example with my mom's little movie night snippet. So the idea here with window size, you want to make it long enough so you're getting a reliable pattern throughout the window, ideally. And so 3 times the length, the longest possible period is what that buys you. Frequency range, in theory, in the old days, if you minimize frequency range, it would reduce computational load. You at least don't want to have it going from like 0 to infinity. You have to have a reasonable range somewhere, so your computer's not just counting numbers forever. And you can change this one to help fix problems like pitch halving or what have you. There's also what is called step size, which is how many steps you take in between each measurement of F0. That just gives you different amounts of temporal precision in the pitch contour you produce. You can't really tweak that one in prot, but in theory, if you're creating a pitch tracker from the bottom up, you could do that. I think I've said enough about this for now, so I'm going to stop there. But as always, you can ask questions through email, D2L, or on this post on YouTube. So hope you enjoyed that. We'll be learning how to apply this practically to the analysis of intonation in our next set of lectures. So see you then.